Good evening everyone. My name is Renu Raman Sahu and today we will be discussing about the sessions of the last week, mostly on Fermi-Dirac statistics, and then we will be solving some of the previous year questions so that you can solve the assignment of this year. So the Fermi-Dirac statistics, it describes the distribution of fermions across the energy levels of for a system in thermal equilibrium. So fermions, so mostly we are talking about the electrons, and the electrons qualify as a fermions because they have half integer spin and they obey the Pauli exclusion principle. So these are the four characteristics. They obey the Pauli exclusion principle. The particles are identical and indistinguishable. This indistinguishability is a characteristic of these quantum particles, and these are subject to the constraints that the total number of particles is fixed and the total energy is fixed. What this total energy is, the fixing of total energy, what it means is that the net energy of the system is constant. So the total energy is neither taken in and net energy is neither coming into the system or away from the system, it is constant. So given these conditions or these constraints, what we want to find is that the probability that a state with energy Ei is occupied. This is what we want to find out in this framework. So, let us say that the system has energy level E0, E1, E2, E3 and so on up to Er, and S0 is the total number of energy states with energy value E0. S1 is the total number of states with energy value E1, and similarly so on. So our system is fixed in volume, so this EIs and SIs, they are fixed. This SI, you can think of it as the degeneracy of EI, or so this can be, so the relation between this EI and SI, this as we'll see later, this will be called the density of states. For a given interval of energy, what are the number of states available? So these two are fixed once our system is fixed. Now we want to find the number of particles. We want to find the number of particles uh, in each of these energy states. This N0, N1, N2. So this we these are not fixed. This can be varied. We want to find what is this N0, N1, N2 in thermal equilibrium. Now that we have a constraint that electrons are fermions and they are quantum particles, this for each given Ni there is a limited number of Ni's, and this Ni cannot be more than Si. So Si is the number, let's say S1. S1 is the number of available states with energy E1, and the number of particles cannot exceed the number of available states. What we want to find is how these states are filled given these constants of the constant total number of particles and constant total energy. Now we'll denote a particular arrangement of the particles in these energy levels as n bar I, a particular set of ni's. And we want to find f of ei. F of ei is the probability that a state at energy ei is occupied. We'll find this subject to the condition that, so if we want to find this, we have to know something called the conditional probability of finding that the energy Ei is occupied given that the arrangement is n bar. So this we can find. So once this n bar is fixed, let's say these ni's are fixed, and we'll look at these values E3, S3, N3. So for this, so S3, what is the probability that the state at energy E3 is filled? We are saying that three particles are filled and these three are not distinguishable. So this is this can be filled. You can think of it as there are S3 boxes and you have to fill with three particles. So you have to choose three boxes out of these S3 boxes, So n3 boxes out of these s3 boxes, and then you have to fill them. So it is the number of way you can choose n3 from s3. So that we'll see later. uh, uh, so the probability that E3 is filled is just N3 by S3. So this probability is can be written as f of Ei by n bar is Ni by Si. Another quantity that we need is the probability that the arrangement is in n bar. So that can be obtained by looking at the number of ways in which that n bar can be created divided by the number of ways in which any other n bar can be created. So, so the probability of the probability that the system is in n bar is the number of ways this ni is created divided by the total number of ways in which any n bar can be created. So f of Ei will be sum over all such terms, sum over all the arrangements for the conditional probability that Ei is occupied given n bar, and what is the probability that n bar is the arrangement. So that is W n bar divided by W total. Now we'll make an arrangement. Now let us say that there exists an arrangement n naught bar for which the number of ways in which n naught bar can be created is maximum. So W n naught bar is the maximum. Now we have learnt in previous classes that the most probable arrangement is larger than sum of all other arrangements combined. So this corresponds to almost 99.9999% of the W total. So that is why this is almost equal to 1. And this was done at the beginning. So for, and if you want to look at the summation that we saw for f of Ei, so this is the probability that Ei is filled. That was the sum over all the sum of this term, which is maximum term, plus sum of all the terms which is not the maximum but the other terms. It turns out that this term is the largest term and all other will be very very small. This W n I bar by W total, this is very very small. So we can neglect this and we'll be remaining with only one term, and here also W n naught bar by W total is approximately equal to 1. So f of Ei is approximately equal to f of Ei into n given that n naught bar is the arrangement, and in this arrangement in which W n bar 0 is maximum, that has the probability Ni by Si that Ei is occupied. So we want to find what is Ni by Si for given n naught bar. So how to get this for a given n naught bar that will maximize? So we'll see that now. Now let us first find what is W n naught bar. It is the number of ways in which the most probable microstate n naught can be attained. So it can be attained by, so n naught is the energy level, s naught is the number of such energy levels, and n naught is the number of particles in E naught. Okay. Now the total number of ways in which W n bar can be attained is product of the number of ways in which each of these energy states is filled. So it is the product of the number of ways in which Ni particles can occupy Si states, which have energy Ei. So that is the question we want to solve. So energy Ei has Si states and Ni particles. Let's say Si is 4. So we have like 4 boxes, and out of that we want to have N2 particles. Let's say N2 is 2. So out of these 4 states, we will choose 2 states to fill the particle with, and that can be done with 4 choose 2 ways. So that is why the number of ways it can be done is 4 choose 2. Similarly, each of these I, it can be Si choose Ni, and we have to take product of that. So the number of ways where Ei can be filled is Si factorial. So this Wi choose Ni, and that is nothing but uh, sorry, that is uh, number of wi of ni is nothing but si factorial divided by ni factorial into si minus ni factorial. So this is how we can fill this ith energy level. Now the number of ways a particular arrangement can be obtained is the of product over all the energy states in into product over all the energy states of what is the number of ways in which that energy state can be filled, and we want to now maximize this. Okay, so we wish to identify an n bar which will maximize w of n bar, which is given by this expression, and that we will call n bar naught, for which w n bar is max, and corresponding to this w n bar naught, what we want to find is ni by xi, subject to two conditions. The first condition is that the total energy has to be fixed, which means that E total is sum over I equal to 1 to, so all the energy levels ni times Ei. And the second constraint is that the total number of particles has to be fixed, that is n total is equal to sum over I equal to 0 to r, which means sum over all the energy levels of ni has to be a constant. So mathematically speaking, what we have is we have to maximize this quantity subject to constant written in equation 2 and 3. This we want to solve, and we were going to take the approach of the method of Lagrange multiplier. So this is the problem statement what we have with us. The probability of occupancy of a state with energy level Ei is f of Ei, which is the sum over f of the conditional probability times the probability that n bar is the arrangement. Okay, the probability of occupancy of a state at energy level Ei when the distribution is n bar into probability that the distribution is n bar. Okay, and we had seen that the probability that n bar is obtained is the number of ways in which n bar is obtained divided by the total number of ways in which any n bar is obtained. So now we assume that there existed an n bar which will which results in the maximum possible value corresponding to w n bar naught. Let's say this is the max value. So there will be other values, like this is another arrangement which has certain number of ways it can be attained. Like n2 bar can be obtained in w n2 bar number of ways, and so on. Let us say that this is maximum value. Now we have seen in previous classes that this max value is more than the sum over all the number of ways in which any other state can be, any other arrangement can be obtained. That is why this w n bar naught, the one which maximizes, divided by the total number of ways in which any other probability, any other arrangement can be obtained, that is almost equal to 1. And given this, what we have is the probability that the energy E is occupied is same as the probability that energy E is occupied given that the arrangement in which the system is in maximizes it maximizes the number of ways in which n bar naught is obtained. So we will now focus on this term and we will find ni by si for this arrangement. So let us first find what is this n bar naught. So also we had seen that w of n bar, it is a product of the number of ways in which energy Ei is filled, and energy Ei is filled in as I choose ni number of ways, and as I choose ni is nothing but si factorial divided by ni factorial into si minus ni factorial. And so this is the product of all these terms, and product of all these terms is just this individual factors. Now we want to maximize this quantity. This is same as maximizing the logarithm of w of n bar. Why we are taking logarithm? Because all the products and the products will be changed to sums and the division will be changed to the subtractions. So when we take the logarithm of that, what we will have with us is sum over I and log of si factorial minus log of ni factorial minus log of si minus ni factorial. So when we take the log, so we have now these terms as log of si factorial, log of ni factorial. We have to remember that this si, ni, these are very large numbers and these are of the order of 10 to the power 23. I mean of the order of the Avogadro's number. So Stirling approximation will hold best, which is nothing but log of n factorial is equal to or is approximated with n log n minus n. So when we expand this using the Stirling approximation, what we have is, and on simplification we'll have si log si minus ni log ni minus whole bracket si minus ni into log of whole bracket si minus ni. Here we have to remember that these si's are fixed and ni's are the variables here. So at maximum, the variation of log of wn bar is 0. So at maximum, if you marginally change this n bar, this log of wn bar or the function which you want to maximize, that shouldn't change. So now when we take the variation over this and variation over this, so there will be no variation for this, so delta of si log si will be 0 because si's are fixed, and here we have to apply a chain rule. For this quantity also we have to apply chain rule. So when we take delta of log wn bar, and we'll end up with this expression, and on simplification what we'll have is this equation 1. So equation 1 is subject to the constraints that the total number of particles is same and the total energy is same. So we want to maximize the equation 1 subject to equation 2 and equation 3. So we have to use the method of Lagrange's method of undetermined multipliers. Let us calculate minus of equation 1 plus alpha times equation 2 plus beta times equation 3. So alpha and beta are the undetermined multipliers of Lagrange's, and when we do that we get sum over I in bracket minus log of si minus ni divided by ni plus alpha plus beta ei, and close bracket delta ni is equal to 0. We want this to be 0 irrespective of any arbitrary delta ni, and that is when we can say that this wn bar is maximum. That is possible only when each of these term is individually 0. So this is individually 0 when log of si minus ni divided by ni is equal to alpha plus beta ei. So when we take the exponential of this, what we will end up with is si minus ni divided by ni is equal to e to the power alpha into e to the power beta ei. And now we take this ni to right hand side, so we have this product of ni e to the power alpha e to the power beta ei, and then we'll take this ni to the right hand side, so what we have is si is equal to ni by ni into 1 plus e to the power alpha e to the power beta ei. And now what we have is ni by si, so we took this si here and this factor to the other side, so it is 1 by 1 plus e to the power alpha e to the power beta ei. It turns out that alpha is equal to minus ef by kBt, where ef is called the Fermi energy, whose significance we'll see in a while. Kb is the Boltzmann constant and T is the temperature in Kelvin. So what we have is f of I is approximately equal to ni by si, that is 1 by 1 plus e to the power ei minus ef by kBt. This particular distribution is known as the Fermi-Dirac distribution. So what it says is that the probability of occupancy that ei is occupied is 1 by 1 plus e to the power ei minus ef divided by kBt. If you plot f of ei as a function of ei, it looks somewhat like this. So it starts from 1. So let us see what happens at t equal to, when t goes to 0. When t is going to 0, this kbt is really very small. So you can think of it as like 0.00001, very small. And ei, let us see what will happen if ei is less than ef. If ei is less than ef, then this is a negative number, and a negative number divided by a very small positive number is a very large negative number. So e to the power minus of a large number, so is almost equal to 0. So f of ei is equal to, approximately equal to 1. So this is what happens at t equal to, when t is equal to 0. At absolute 0, when as soon as you have this energy less than the Fermi energy, you have f of e is equal to 1. Now if you have this ei a little bit more than ef, then this is a positive number, and divided by kbt. Kbt is very small, so it is e to the power plus infinity, which is a very large number. Okay, so 1 by a very large number is almost 0. So that is why we have f of e is equal to 0 for e greater than ef. Now what will happen at higher temperatures? As at higher temperatures, this f of e will reduce, it will become less than 1 till some values, and then it will approach to 1 if you lower in energy further. And at higher energy it will become a little positive, more than 0, and but at still further, if you are too further away from the Fermi energy, the probability of occupancy is 0. We can think of this EF as the highest energy available to the system at 0 Kelvin. At 0 Kelvin, what we have is all the energies are filled up to EF, and after that nothing is filled. So the highest energy filled at 0 Kelvin is called the Fermi energy, or if you see all these plots, then all these curves pass through point 5. So if you look at this expression, when ei is equal to ef, f of ei is 1 by 1 plus 1, which is 1 by 2. So at whatever the temperature you are in, if the probability of occupancy of that state is 0.5, then it is the Fermi energy. So energy whose occupancy is 1 by 2 at t greater than 0 Kelvin is the Fermi energy. Now one thing we can think of it as what this Fermi distribution tells and what it doesn't say. Let us say that we are looking at energy of a jar, and we want to, if we want to say what is the probability that water is filled at a height h less than this topmost height. So it is 1. So the probability is 1 till this highest water level, and then the probability becomes 0. So you don't find any energy. And this is the situation irrespective of the shape of the material. Okay. Now, if you look at this analogy of these pots, we know here that if you want to ask this question, what is the amount of water at height h? H is less than this highest h, or the Fermi h. So we know that the probability of occupancy of this height is 1, but we don't know how much water is there at this height. To know the amount of water at this height, what we have to know? We have to know what is the shape of this object. So if we know the cross section area of this object, then of the pot or the vessel, then we know the amount of water it is holding at that particular height. Similarly, if we want to know the number of electrons at a particular energy level, then what we require is to know what is the number of states between this particular energy interval. So that quantity is called this density of states, or in other words, we need to know how many states are there for energy ei. That information about density of states is necessary for us to understand what is the number of electrons occupying a particular energy level EI. So we'll look at some of the differences between this Maxwell-Boltzmann distribution and Fermi-Dirac distribution. So Maxwell-Boltzmann distribution is given as this Ni, the number of particles which is at energy Ei, is N by P, P is the partition function, E to the power minus Ei by kBt. Or in probabilistic term, what we can write is P of E equal to P naught E to the power minus E by kT. With increase of temperature, you see this red one is the less temperature one, and as you increase the temperature, then the probability of the higher energy increases, it keeps on increasing. Moreover, the probability of each of these energy levels is increasing with increasing temperature. What it means is that electrons at all these energy levels are getting excited or taking energy. So we'll look at the corresponding situation in the Fermi-Dirac distribution, but let us look at some of the some of the differences between Maxwell-Boltzmann distribution and the Fermi-Dirac distribution. The Maxwell-Boltzmann distribution applies to a collection of classical particles, whereas the Fermi-Dirac distribution applies to a collection of fermions. And classical particles are identical and distinguishable. On the other hand, the Fermi-Dirac statistics applies to identical and indistinguishable particles. The fact that we derived Fermi-Dirac statistics relies on the fact that the particles are indistinguishable and electrons the particles follow the Pauli exclusion principle. In Drude model, so the model here is called the Drude model in case of Maxwell-Boltzmann. In case of Fermi-Dirac, it is called the Drude-Sommerfeld model, because Sommerfeld is the scientist who used the Fermi-Dirac statistics to solve the anomaly, some of the anomalies of the Drude model. So here we see, as we increase the temperature, all the electrons at all the energy levels raise up to higher energy level, or raise up in energy. On the other hand, if we have this Fermi-Dirac statistics, the electrons only nearer to the Fermi energy get excited to higher levels. So not all the electrons are taking energy, only some electrons which are near the Fermi energy are taking the energy and getting excited to a higher state. So if you look at CVE, the electronic contribution to the specific heat, what will Maxwell-Boltzmann predict? Maxwell-Boltzmann, it predicts that for a given change in temperature, Maxwell-Boltzmann distribution requires us to give energy to all the electrons of the system. On the other hand, what we have in Fermi-Dirac system is that it has the limited number of states and a limited number of electrons. So at 0 Kelvin, all the levels up to EF is filled, and as soon as the temperature becomes T greater than 0, then not all the electrons can raise up to higher level. For example, the thermal energy delta is delta E, which the electrons are taking. If the electron is deep underneath this Fermi energy, then and they want to transit up to some higher energy kBt. But if that state is already filled, then those electrons cannot take those energies. The only way in which the electrons can take energy is there has to be some empty state at with energy delta E further away, and that happens only to the that can be attained only near the Fermi energy surface. So what we see here is not all the electrons take the thermal energy, only electrons near the Fermi energy will take the energy and get involved in this thermal processes. So this is one of the major difference between the Maxwell-Boltzmann and Fermi-Dirac statistics. Another key thing is that these distributions are not same. how many electrons are participating in the energy exchange. To know how many electrons are participating in this energy exchange, we need to know how many states are there per unit energy. And to find this density of states or numbers, the number of states with each energy level, we need to incorporate the effect of ionic force. So that is nothing but this potential versus position, uh, the potential as a function of position. From there we can get something called the density of states, and once that is there, we can calculate the number of electrons participating in any process. So that is the gist of all the stuff that was taught in the last week. Based on that, we will solve some questions and answers. So let us look at the first question. If the system is under thermal equilibrium, in case of Fermi-Dirac statistics, then it assumes, let us see at each of these options. So the first option, it says that the system has a constant total energy. So thermal equilibrium is, it is in, the system is under thermal equilibrium. Thermal equilibrium, it itself means that E total of the system is constant. So this option is correct. It has the constant total energy. In case of Fermi-Dirac statistics, we have taken that the number of particles has also to be constant. So this is correct. The change in total energy, so delta of total, this is the change. Delta E total is equal to 0. Similarly, delta N total is equal to 0. So the change in total energy and total number of particles, that remains 0. That is because these are constant. Follows from the first two options. The system has varying energy but constant temperature. So this cannot be true, because if the system has varying energy but constant temperature, that means the specific heat is so C is dou E by dou T. So that means the specific heat is infinity, which is not true. So if it is varying energy, it needs to have varying temperature as well. So this statement is wrong. If the total energy of a closed system is constant, that means, so in a closed system the total energy is constant. From here we can directly conclude that delta of E total is 0, because derivative of a constant is 0. So change of energy will be 0. What are the other options saying? The particle numbers keep on increasing. It is a closed system. The particle number cannot increase. The very definition of closed system is that the particles cannot, the number of particles cannot change. So neither the particles can go out of the system, neither it can come into the system. So the second option is that the product of total number of particles at each energy level remains constant. So it is suggesting that EI and I is equal to constant, which is not true. What is true is sum over Ni equal to constant, not the product. The system is being heated steadily. So if the total energy of a closed system is constant, that means it is in thermal equilibrium. So if it is being heated steadily, then it is not in thermal equilibrium. So this is not the correct answer. In Fermi-Dirac distribution function, f of Ei is equal to 1. So we have to find out when is f of Ei is 1. We can directly see from this figure that f of Ei is 1. Let's say for t equal to 0, we have to follow this red curve. At t equal to 0, if energy E is less than Ef, it is already f of e is already 1. So e less than ef and t equal to 0 is the correct option. And at t goes to 0, when it is when f of e is 1, only when energy is really less than ef. That means e is less than ef and t goes to 0, then f of ei is 1. So while in the other case, if e is so this will imply f of ei, e is greater than ef and t goes to 0. So at in those case, if you follow the graph, this f of ei should be 0. So this statement is wrong. And e greater than ef at t equal to 0, then also if e is greater than ef at t equal to 0, then also you cannot have the value of f of ei to be 1. So for here, f of ei is equal to 0. The probability of occupancy of states by fermions. Uh, so we have to again look at this plot. So f of ei always is 1 always. This is false. F of ei is 1 if ei is less than ef and t goes to 0 if t is, so then only it is 1. Okay. And f of ei equal to 0 always, it is never always 0. And f of ei is less than 1 for ei is a bit less than ef for some values of energy. And let's see, this is ef and okay, and this is f of e. F of ei is less than 1 for energy ei is less than ef. So this is true. This is true because here it can come down and go here like this. So here f of ei is less than 1 and it is greater than 0 here. So this statement is true. This statement is true, this statement is true. F of ei is greater than 1, it cannot be greater than 1. And f of ei is less than 0, it cannot be less than 0. It is between 1 and 0. The Fermi-Dirac function f of ei becomes half. It becomes half when you are at a non-zero temperature and your energy is equal to ef. So here f of ef is 1 by 2, here it is 1. So t greater than 0 and ei equal to ef is your correct answer. So this is what we discussed. So what is the probability of occupancy of states by fermions in a solid at a temperature T greater than 0? So we have to follow this curve where T is greater than 0, and we can see that f of ei is equal to 1 always, that is false. F of ei is, so this is what we just discussed just now. Now we will go to this question. A system containing energy E1, E2, E3 to En have states 2, 7, 9, so on 14, and number of particles 1, 5, 3, 5 respectively. And in how many ways you can arrange the empty states alone in the energy level E3? Okay, so let us look at E3. There are 9 states and 3 particles. So the number of empty states is 9 minus 3, which is 6. So number of ways in which these 6 empty states can be arranged by simple combination and permutation, it is just 6 factorial. It is like you are already given 6 states. Now find how many ways you can arrange them. It is just like you have a square. Let's say you have 3 objects. The number of ways in which these 3 objects can be three objects can be arranged is 3 factorial. How? Let us say that we have a square, triangle and circle. So this is one way, this is another way, second way. Now the third way is this, and third way is another way is this, and this can also be a possible arrangement, and this is another possible arrangement. So these are the six ways in which we can arrange these three states. Similarly, if we have six states, we have to go by 6 factorial, and 6 factorial is nothing but 720. So 720 is your correct answer. Now, what is the maximum number of arrangements possible in energy level E3? So we had E3 and S3 is equal to 9 and N3 is equal to 3. The number of ways in which this can be obtained is, this is similar to the question. You have 9 empty box and you have 3 particles. So in how many ways you can put 3 particles in 9 boxes? The number of ways you can do that is you have to choose 3 out of 9 boxes and then you have to fill them. So that can be done in 9 choose 6 ways, which is nothing but 9 factorial by 6 factorial divided by 3 factorial and 9 minus 3 factorial, which evaluates out to be 84. So 84 is your correct answer. So what will be the conditional probability at energy level E3 in question 1? So E3 has S3 and N3, S3 was 9, N3 was 3. So the conditional probability f of E given n bar is N3 by S3. So this is E3. N3 we know 3, S3 we know 9, it is 1 by 3. So your correct answer is 1 by 3. The most probable arrangement is, so we had seen that we had written the, and let n not be the most probable arrangement, and so the number of ways in which the most probable arrangement can be obtained is significantly larger than the next most probable arrangement, and all such next most probable arrangements combined. So that is why the first option is correct. The first option, what it says is, the first option is this. It is significantly larger than the next term and significantly larger than the sum of all the terms. So this is also correct. And since it is very large, and therefore it can be considered to be 1. So that is also true, because W of n bar naught by W of n total is equal to 1. Now let us go to the next question. So again this question is from this Fermi-Dirac plot. So at t equal to absolute 0, let us analyze all the questions. So for option A, at t equal to absolute 0, we have to follow the black curve in this diagram. So the first option is f of e is equal to 1 when e is less than ef. So for this region, for all these regions up to this ef, so f of ei has value 1. For all the energy E less than ef, which is true, so A goes with 1. So this is true. And f of E equal to half when E is less than ef. This statement is wrong, because whenever E is less than ef, so E is less than ef, you see all the f of E is more than half. All the f of E is more than half. So the second option is false for A. And for the third one, f of E is equal to 0 when E is greater than ef, which is true. You see this at t equal to 0, if you go a little bit more than this ef, you don't have any occupied states. So f of e is equal to 0 when e is greater than ef, which is true, and so a goes with option number 3. And f of e is half when e is equal to ef, which is false at t equal to absolute 0. At t equal to absolute 0, f of e when e equal to ef is 1. Now let us look at the option B. T is greater than absolute 0, which means we have to follow this green curve here in this diagram. And here when the fourth option will be correct, because f of e is equal to half when e equal to ef. When e is equal to ef, f of e is half. That is clear from this plot. So your correct answer will be option number 3. And had there been another option, this a goes with I and b goes with 4th, and that would also have been the correct option. Now let us look at question number 6. So the probability of occupancy f of e versus the energy plot of Fermi-Dirac distribution at absolute temperature has all the information of electrons, except it cannot say anything about the shape, the number of states of the occupied electrons. So if you remember the pot analogy, the number of states is analogous to the shape of the pot. Okay, it, it has some information about the energy of the electron, so this is not the correct option. The highest energy level also the information is there in terms of Fermi energy. The density of allowed state, this is what we don't yet know. This we don't know now for Fermi-Dirac distribution. So your correct answers are 1 and 4. F of E at the Fermi energy of collection of fermions at minus 270 degrees Celsius. So minus 270 degrees Celsius is nothing but your 3 Kelvin. At 3 Kelvin means we have to follow this green curve. So here we can see that f of E is always less than 1, irrespective of what is the temperature, or irrespective of all the temperatures, it is always less than 1. It cannot be greater than 1. It is equal to 5. If it is equal to 5 only if E is equal to EF, and it is greater than 0.5 if E is less than EF. So since these are not universally true, we cannot take that. The correct answer is less than 1. Which anomaly of Drude model was corrected by applying Fermi-Dirac distribution? In Drude model assumed the distribution to be like this. So this is Maxwell-Boltzmann distribution, and all the particles, you see, all the electrons will have to be excited if we want a unit change of temperature. Whereas in Fermi-Dirac statistics, what we have here is only a small fraction is excited. So on increasing the temperature, only this small fraction is excited. So that is why this predicted a specific electronic heat capacity at constant volume at Drude is almost 100 times more than the normal Drude model, the Drude-Sommerfeld model. Okay, so that is one of the key steps towards understanding that the electrons are indistinguishable and they follow Fermi-Dirac statistics. In classical Drude model, only few particles participate in gaining energy. This is clearly false. Why? Because in classical Drude model, it follows Maxwell-Boltzmann statistics. And Maxwell-Boltzmann statistics, it says that there is no limit to the number of particles for a given energy level. So we can fill indefinitely, and when you do that, it is a classical particle, and we saw that it has anomaly in the specific heat. So that is the reason why this particular statement is false. So the Drude Sommerfeld model, what it did, it incorporated Fermi-Dirac statistics, and what it assumes is that electrons are fermions. Yeah, that is why you can apply the Fermi-Dirac statistics. It assumes all particles are identical. Yeah, because all the quantum particles are identical and indistinguishable. It assumes all fermions in solid participate in the process of gaining energy. This statement is wrong. Why? Because it is not all the fermions. They are constrained by the Pauli exclusion principle. So it assumes a very few fermions, only very few fermions participate in the process of gaining energy. That is true, because here if you see this plot, it is only some electrons near the Fermi energy which contribute to the heat capacity. And here what we see is that these particles which are at just energy level nearer to this EF, they will just get excited to the higher E. So a very few fermions participate in the process of gaining energy. So thank you very much for joining. We will meet next week. I hope this discussion of question and answer was helpful to you. We will meet in the next class. Thank you.